Hello, hello. Thanks for coming today. Thanks for choosing this talk on model calibration. Calibration is the alignment of models' confidence outputs with the actual probability of the output being correct. A few words about me first. I'm a full-time ML research engineer at DSC and a recent data science graduate from FER here in Zagreb. This is my third time on the data science conference, twice here and once in Belgrade. So what I will talk about today is I'll motivate this model calibration, in general, why we need it, how to measure it both numerically and visually, are modern neural networks calibrated out of the box or not, what are some simple post-processing calibration methods, something about generative calibration, and then we'll wrap everything up. So first of all, why would you need model calibration? Let's say you have a simple vision classification model that outputs vector y of softmax outputs, and it has n classes, for example. Well, in order to choose the correct class, you would just take the argmax, and in order to choose the confidence, you would take the max of this vector, right? But if we get the confidence of 0.7, for example, what does this mean? Does this mean that this model, this prediction is 70%, it has a 70% chance to be correct? Well, ideally, yes, but in practice, no. Because in practice, what we see is on the right, and ideally, it would be the pink thing where we have the confidence and accuracy aligned in each of the bins. However, usually, it's the thing in the blue, which means that the model, in this case, is overconfident. We can see that for the confidence bins of around 0.6, it has the accuracy of around 0.4. And why would you want to have the calibrated model? Let's say you're operating in a high-risk field, such as automated healthcare, and if you have a calibrated model, then for low-confidence predictions, you can just leave it up to a human expert. For self-driving cars, if you don't know whether to brake or not because it's a low-confidence prediction, you can just leave it up to some other system to decide, not AI. And nuclear energy is another field which needs really, really calibrated models. Now, what are some potential applications when you have the calibrated model? First of all, you can filter the predictions. That's what we do as a document understanding company. If we need to identify the signature and we have a low confidence output, we'll simply tell our client, hey, you might want to check this. Maybe there's no signature or there's something wrong with it. Then you can do model-aware active learning, which means, okay, we've deployed our model and we collect all of the inputs now during inference which have low confidence. We take those to the side, we label them, and then we do active learning with only those. And finally, you can detect difficult or out-of-distribution data. Well, this is intuitive. Maybe you have trained your model for example, typewritten data, typewritten text, and then you get something that's handwritten. Probably you will have a low confidence output, and this because it's out of distribution. Well, now, how to measure the calibration or miscalibration? First of all, numerically, most common method is the expected calibration error. As it says, it is the expected metric. It's not completely 100% correct, but it's the expected error. Again, we have bins. Let's say there's 10 bins. Into each bin, there goes the confidence output of the model. And then for each bin, apart from the average confidence, we calculate the accuracy in this bin. That's A and that's C. Ideally, these two would be correct, right? If the average confidence is 50%, we'd also like the accuracy to be around 50%. Most often, it's not. So we subtract those two. We just weight it with the bin size and sum everything up to get the expected calibration error. This is a better way of calibrating miscalibration. We can also showing it. We can also visualize it. However, here you can notice that we don't have the information how many examples are inside each of the bins. We only have the example, what's the confident, we only have the information, what's the confident and what's the accuracy. But this is how you would visualize whether or not your model is miscalibrated. Now, modern neural networks, out of the box, are they calibrated or not? First of all, we will not go so modern. We'll take a look at the ResNet, which was published in 2016, and compare it to a very old, small 5-layer network, LeNet, from 1998. In the first row, we can immediately see that the average confidence and accuracy of LeNet are pretty similar, which is good, whereas the average confidence of ResNet is much larger than its accuracy. We can also see that for ResNet, almost around 60% of the predictions are 95% plus confident, which is a lot because it still has a decent amount of error. And in the second row, we can see that, yes, LeNet generally on this reliability diagram is better calibrated, a bit underconfident, whereas the ResNet is worse calibrated and a bit overconfident. Now, what people usually just look at is this error on the bottom, which says, yeah, ResNet has a smaller error, whereas LeNet has a higher one. And that's what usually people pursue. And that's great, but then you cannot really trust your confidence outputs, as we can see. Now, how has this been observed through the architecture? We'll take a look at some different aspects. First of all is the depth, how many layers there are. And we can see as we increase the number of layers, as the ResNet is larger, okay, the error is smaller, but also the calibration is worse. Then as we increase the width, which is number of filters per layer, again, the same scenario. The error is smaller, but again, we are miscalibrating the model. Then regularization technique, which is batch normalization. With it, yeah, smaller error, but worse calibration again. And weighted decay, which is another regularization technique, which is not that popular anymore because you can use normalization, batch normalization, dropout, and some other techniques. But again, with this, we get better calibration, but it's not that used anymore. Another observation is when we take a look at the training and the test error and the loss function. On the epoch 250, we have the reduction learning rate. That's why there is a jump. However, you can see, and what usually people pursue, is this reduction in the test error. And it does decrease over time, over those 500 epochs, almost all of the time. Whereas the test loss function actually starts increasing at some point, which means that the model does not overfit on the accuracy or on the 0-1 loss, but it does overfit on the probability distribution. It does overfit on the confidence. And that's why when evaluating your model, you should probably take a look at the loss function and not the F1 score or recall or whatever you're interested in, actually, because these drop in maybe 1 or 2% in error is maybe not worth this huge increase in the loss and in miscalibration of your model. Now, a bit more recent architectures, transformers. Well, good news, they are better calibrated out of the box. And we can see that in the first row, where we show the in-domain calibration. That means you train and evaluate your model on the same set, just different splits, same task. Whereas out of domain means that you have the same task, but maybe different domain. You train it on the tweets, and now you evaluate it on some medical data. When we take a look at the in-domain, and here we're taking a look at the text class, text tasks, not vision anymore. Yeah, we can see that among the same model family, which is BERT and Roberta, they have the same architecture. Roberta still performs better. So it's not all about the architecture at the end of the day. Why? Roberta has more data that it's been pre-trained on. It was pre-trained for more steps, and it has dynamic masking instead of static. So we can actually achieve better calibration with not only architecture, but some other methods. When we take a look at the out-of-domain data, well, the maximum likelihood estimation, which is what you usually use when minimizing your loss, which means, okay, this is a correct class, we want to spike this confidence up and put everything into 0. Well, it doesn't seem to be that great out of domain, which makes sense. And what seems to be better out of domain is label smoothing. And that means that you don't want to spike the correct class and put everything else to 0, but you want to smooth it out. And that actually makes sense when you observe out-of-domain data. However, most of the time, you're not really completely sure that the task that the model was trained on will not be the task that you evaluate it on. You cannot be sure that you will test it out of the main. So just something to keep in mind. Now we'll go back to the vision task, ImageNet, and we'll compare different families. So first, there is an MLP mixer, which is multi-layer perceptron only. Then we have the vision transformer, and then we have the BIT, which is the resonant-based architecture. I'd like to focus only on those three. On the right, we can see that the size of the symbol indicates the model size, actually. The larger the symbol, the larger the model that it was trained and evaluated on. So first, taking a look at the BIT, so the square, orange square, we can see that, yes, the larger the model, the better the ImageNet error, but the worse the calibration error. That's something we've talked about a few slides before. So here it's very clear that by reducing this model size, we actually get a higher ImageNet error, but we get a better calibrated model. Whereas for the vision transformer and for the multi-layer perceptron, it's not that clear, right? We see that they do perform better than the resonant architecture, and we can see that these two perform similarly, but it's not that clear that by increasing the model size, you get actually better ImageNet error and worse calibration error. But the conclusion is that the architecture and the family of the architecture is very important in understanding whether or not your model will be calibrated out of the box. Now, what are some very simple post-processing techniques that one can use to reduce this miscalibration? And they really are simple. There's more, but I will just state these three. Histogram binning and isotonic regression are somewhat similar. For histogram binning, you have M bins, you have their limits, and now you just try to optimize this theta M for each bin limit, which basically means that you will try to set this theta for the bin at the ratio of positive examples in the bin. Regression very just also optimize the number of bins and the limits of the bin. And what's very important to notice here, that the binning and isotonic regression actually might change your predictions. So if you predicted that the correct class is cat, this in some cases might change the prediction to a dog, for example. And since you've trained your model for many epochs, you use your hardware, and then you do some simple post-processing technique which changes your predictions. Well, for us, we've found that sometimes this change is not always on the better, it's sometimes on the worse. That's why I don't like the first two techniques that much. They might help with calibration, but they sometimes also increase your error. Whereas temperature scaling, if you take a look at it, well, the prediction output is scaled with this temperature that's found on the validation set, and everything is scaled proportionally, which means that your predictions stay the same, only the confidences change. And this is great, because you're still sure that what you trained, your predictions are the same. But if you were underconfident, you can increase your confidences and vice versa. And that's the approach that actually is the simplest and works in literature the best for most of the cases when tested empirically. Now, generative calibration. So far, we had a problem with maybe 10 classes, 100, or even 1,000 with ImageNet. But what happens if we have 50,000 classes, which is what generative calibration is? Because at each step, you are predicting the next token, and it can be one of maybe 50,000 tokens from the vocabulary. Well, we cannot have the same approach. We need this sequence likelihood calibration. Now, to introduce this, let's first talk about this loss function, which is basically n examples, and then at each time step, you're predicting the next token, where you have the input and the previously generated tokens, and you do this for all of the time steps that you have. And what's been found is that 4 things help mitigate some of the problems. First is the one that I've mentioned, label smoothing. And here, if you think about it, it makes much more sense. If the sentence starts with, I like my, and actually in the text it says cat, well, okay, but we don't want to spike the confidence of cat and put everything else to 0, because in reality it can be I like my family, I like my car, dog, whatever. And then here in the generative scenario, it makes much more sense to actually smooth out the labels. Then decoding technique, again, you don't want to just greedily take the next token every time you see it. That's the most probable. No, you want to have some techniques such as beam search to keep track of the most likely sequences, multiple ones. Then length normalization, if you just take a look at this formula, you can see that actually shorter sequences have then the higher probability, right? And we don't want that. So we also should normalize this length. And finally, generative models have this problem of repeating their tokens, and then there is a technique such as trigger and blocking to prevent this. But how to actually calibrate the generative models then? Well, first two steps are the ones that you are all probably familiar with. You either pre-train on some data set, or you take the pre-trained weights, which most of us do. Then when it comes to fine-tuning, this is, okay, you label your training set. For us, this was the TrOCR for recognizing the hand and typewritten text. It can be any other, and you train it for the next token prediction loss. Now comes the interesting part. You take this decoding technique, such as beam search, you decode, for example, 10 candidates for each training example from this fine-tuned model, and you set those to a side. Then you initialize your model that you will calibrate, and then you calibrate it using calibration loss and the regularization loss. Now we'll take a look at the recipe that you need to calibrate your model. First, since you have those 10 candidates, you need a similarity function how to compare them, right? It can be something intrinsic, such as last hidden layer of the decoder, or it can be something external, such as character error rate or rouge metric or whatever. Okay, now you need the actual loss function, which you will minimize and which takes into account the similarity. Well, you can either just optimize the ranking, so we'd like to put the most similar one to the ground truth first, or you can optimize the margin between those similarity functions. Then the regularization loss. Since we've already trained the model, we don't want this calibration to diverge too much from the original task. That's why we might want to regularize towards the gold label that we have, that's cross entropy, or towards the fine-tuned weights, that's KL divergence, depending on what we want. And finally, the decoding method, there's multiple. You probably would go with beam search because it's the best, but there are also others. Now, some takeaways from this generative calibration is that these calibrated models do not require the heuristics that we saw 2 slides ago anymore. So no different number of decoding examples, no label smoothing, no trigger blocking, length normalization. It seems that they don't need this anymore. Also, benefits persist as the model size scale up from 50 million to 2 billion, and their experience actually match or exceed state-of-the-art results on all of the data sets that they've tested on for the huge Pegasus 2 billion model parameters model. The things that you can see on the picture are very average scores across all 4 data sets and geometric means across all Rouge 1, 2, and L scores. But you can see that the benefit of calibration is persistent, and it's persistent as the model sizes also scale up. Now, to conclude everything up, what I tried to do here is actually motivate you to include the calibration error metric in the evaluation of your models. Just as you use the F1 score or accuracy or precision or recall or whatever, it's not difficult to add the calibration error. It's very simple to implement. Also, temperature scaling, something that does not hurt your predictions, and it can only calibrate them better. Simple to add to the pipeline, often most effective, and it really cannot hurt your predictions. Now, when it comes to recent architectures, it seems that transformers are better calibrated out of the box compared to convolutional networks, which is great, even though they do seem like a black box, but I personally would trust more a model that says actually correctly how confident its output is, and this is aligned with the actual probability of the output being correct. And finally, generative calibration seems to always be effective. However, I must say that it was difficult to implement. The paper that I'm referencing here, it does not have any code base published. Also, there's no public library that just says how to do this. It gives you a recipe, it gives you a one-liner. No. So you actually have to go through in the source code and change this. But there were benefits for us. So, well, you decide whether or not this is worth it. Well, with that being said, thank you for your attention. And if there are any questions, we can discuss them. There's also a talk, if you liked the topic, maybe you didn't because there are no questions, but there's also a talk at 11:45 about the conformal predictions, which is a very similar topic, but they just do it differently. So they have not one prediction, but maybe an interval or a set of predictions in order to be more certain into what they're giving out to the clients. So that's a different approach to the same problem, very interesting, if you like the topic. I do hear you. Maybe I can repeat the question.
Yeah, thank you for talking about this and raising the awareness that these deep learning networks that we use every day and more are not that well calibrated like maybe before. Older networks, yeah, smaller ones.
Yeah, until there's no incentive, like for us in the company, there was incentive. Like the client wanted to know how certain we are in our predictions, and then there is an incentive. So I believe that when there is incentive, people would do it, and I'm glad that the field is being researched more. But in this generative scenario, as I said, you cannot find something that's already implemented, and I think that's a big blocker for a lot of people.
I have another question. Could you recommend, please, some concrete libraries in Python which allow to do everything you mentioned? Particularly, I'm interested in these methods for generating models.
Yeah, as I said, unfortunately, the paper is from 2022. It didn't have any code with it. So what I did is I literally went into the Hugging Face source code, and I was looking at the paper and interpreting it and then changing some of the lines. And then this is a bit more difficult to maintain. We didn't raise any pull requests because I don't feel it's that ready to raise a pull request to add this feature, because you're never 100% certain that you did something the way that Hugging Face would do it. But that's the problem with the generative calibration. It's a better technique, more sophisticated than the temperature scaling, but it doesn't have any implementations currently.
So this is maybe more a question from practice. I have recently been exploring implementations in which I use data which was external to the actual model for calibration process. So after I have model inferences, I combine it with some additional information such as data origin or timing, whatever, something that didn't make the model, but I use it for the calibration process. Do you have any experience with something like that?
No, but I've heard about the techniques where they maybe overlap two images and then make the class not just like a single one, but the combination. And that's that's a different way of calibrating these models. I'm not sure how it would work in generative scenario though, but it's one of the techniques, yeah, and I haven't tried it. No, I haven't.
Okay, yeah. Thank you very much, Tin. Thank you very much for all the questions.